Hello, my name is Nabil Al-Hamal. I'm a student in the California State University East Bay Computer Science program. Um, and I'm presenting a research paper I went over called Pascal Weighted Genetic Algorithms, a Binomially Structured Recombination Framework. And so I've titled my presentation Pascal Weighted Recombination Operator. So this Pascal Weighted Recombination is going to be a PWR from now on, is a family that is introduced in this paper. I am going to focus only on the binary convergence. So it essentially uses a weighting scheme that is based on binomial coefficients, and it is doing this specifically for the recombination of a genetic algorithm. I've also implemented this PWR operator to an existing genetic algorithm project I wrote a little bit ago. The author also states that the PWR is useful if a solution needs smooth heredity, stable convergence, and controlled variance in continuous parameter spaces. It seems like the two-parent operator doesn't necessarily give you these things. So the basis of this is the Pascal triangle. We are essentially trying to get weight coefficients that are going to be evenly distributed. And for the rest of this talk, I'm going to be using the example of this row 5, where we use these coefficients 1, 4, 6, 4, 1. Essentially, by using the triangle, we can generate the coefficients that are going to be weighted in such a way that you have most of the weight in the center going out, so that by the time you get to the very end, those have the smallest weights. So the index locations for the row and column are also picked by, here's the row that will represent which one we will use, and it is going to use basically the number of parents in the selection to select which row number we're going to use, and the column is just going to be dependent on which parent we are selecting a gene from. Now, given a couple of things, that let's say M is a set of parent vectors, P1, P2, all the way to PM. Let's also say that W is the weight of each one, and I is the index. And we will say that O is the offspring operator. So in this multi-parent recombination method, we are essentially going to use all the parents in the set to generate one offspring. And so the weights will accumulate, so we will have a summation of the weights with the parent allele. Okay. So to derive the weights, we are going to be using a choice. So this formula is indicating that the weight of whichever index we're using is going to depend on the m minus 1. So if our index starts from 0, m minus 1, and that will give us, let's say we're using the example of 5. Okay, so 5 minus 1 will give us 4. So we are at row 4, and we will choose this row. And out of this row, the index I is going to decide which which coefficient we're going to use. And in the denominator we have a 2 to the m minus 1, so 2 to the 4. And so this will indicate that we will have these 5 coefficients, and they will be they'll be placed in the weights in such a fashion, and we will divide by this denominator. So by doing it this way, we have the weights as shown, where the largest weights are in the middle and the smallest weights are on the outsides. And the interesting thing about this is if we sum up all these weights, we should get 1. That way we're not skewing any of the values. Okay. So in the paper, the algorithm is essentially set out exactly like this. This is a copy from the document itself. And so what it's saying is the input should be that parent set, and we can have a mutation rate that we can talk about later. It's it doesn't really affect things other than since I already have it in my algorithm, I'm not really discussing it because the main focus is the multi-parent recombination here. The output is going to be the offspring O, and so we're going to go through these steps where we will compute the weights first. After computing the weights, we will shuffle the parent order. That way the order doesn't give any positional bias. So each time that we generate an offspring, we will just reorder the parents from whatever set we got them from, and we will recombine that way. See, we will also compute the offspring, and we'll go over the algorithm of how, or the process of how we are going to compute this offspring. And we can apply a mutation algorithm, and finally return that offspring. For real coded genetic algorithms, let's say vectors that have actual numbers, this is pretty straightforward. You have the weight multiplied by the number that will give you a result. You add up all those numbers, and those numbers will become part of the offspring's allele or gene. Okay? For binary, there is a little bit of work that has to be done in the logit space. Now, as this algorithm is proceeding, the recombination is happening here. The weights, let's say, are being assessed for each parent. Okay? So there's 5 parents, there are 5 weights associated with them. At this stage, the assumption is that the parents have already been reshuffled, so their order is not in the same order that they came. The weights are already calculated based on this computation. And we are going to go through a process that will go through one allele or one gene at a time. And the resolution of every parent's allele will add up to become a solution for the offspring. And we will iterate through this until we get all of the parents' alleles into the offsprings, and then we can return the offspring. Okay. Now, because we are working, because my algorithm is working with binary numbers, I'm focusing on the binary portion of this. So we can't use zeros and ones with weights. Essentially, if you multiply a weight by a 0, you will get a 0, and if you multiply a weight by 1, you will get some fractional number between 0 and 1, but not quite 0, not quite 1, and we can't really use that as a binary number. So the strategy here is to use a probability instead of a binary. So we will put that binary value into some function that will do this. If it's a 0, you will get an output of, let's say, something that's really, really small but not quite 0, 0.0001. And if you put a 1, you get a 1 minus a p0, so 0.9999. That way it's almost 1, but it's not quite 1. And now we have something that can be useful. The next, so while we're working in this logit space, we're basically using the inverse of the standard logistic function. So we're going to go through these 5 steps of converting the bits to probabilities. We're going to convert the probabilities to logits. We are going to compute the weight sum of those logits. So if you compare it to what we're doing in the real with real numbers or the real space, we can get we're not doing any of this other than computing the weight sum. So all right, we're computing the weight sum. Then we're going to convert that sum to a probability, and then we're going to convert that probability to a bit. And so we'll go through those processes right now. First step is to convert bits to probabilities. We already went through this. A function that has a 0 will give you this value, 0.0001, and a function that has a 1 will give you a 1 minus a function of 0.9999. So the big deal here is with the zeros that we don't get a division by 0 error and we don't get a log of 0 error. So we are avoiding all of that. And to the right, this is how we've updated the that diagram. So we're still on the first allele, on the kth allele, the k1. We have applied this function, so our zeros are now this have this 0001 and 0.9999, and so we have those values here. Still, so we see that there's nothing with the offspring yet. Second step, we are going to use the logit function, which is the inverse of the standard logistic function. And essentially what we're doing is we're putting those probabilities into this function, and we're getting out a number that is going to be either this, if it's a 0, if it was a 0, is a negative 3.99999, and the same with if it was a 1, it'll be a 3.99999. Okay, and we have also updated the sheet so we can track the progress. Now we will sum the logits that we just calculated, but we'll also multiply each one by its corresponding weight. So like we saw before, it will be W1 multiplied by this logit, plus W2 multiplied by this logit, plus W3 multiplied by this logit, etc., etc. And so the sum of the logits is this number here at the bottom. And so we have 2 more steps to go through before we get an output to this binary value. So we're going to convert the sum of that logit to a probability, and now we will use the standard logistic function. Essentially, we're going to put that weight into the exponent of e, and we're going to negate it, and we should get out a value, and we have something here that is slightly less than half. So 0.4999, 0.00012. And now we need to convert this probability to a binary value. The way that was recommended by the paper was essentially to use a Bernoulli distribution. In the Excel sheet, I did a calculation with binomial distribution. There's a function on the Excel sheet with a binomial distribution, but the Bernoulli distribution essentially is the same, except instead of many trials, you only use one. And so the output using that distribution gives us a 0. In my program, what I ended up doing was, instead of using this Bernoulli distribution, I just used a random number generator and basically had it go if the number generated between 0 and 1 is at this level, if it is the same as what has been calculated here, then this number is going to be a 1. So that just because it's a probability. And if that random number gives us a 0 or is higher than what is here, then we get a 0. So that was a small change that I made to the program to get this going. Okay. And so I have I made this flowchart to show the two-parent algorithm, and basically there's very little difference between this and the PWR algorithm, and the difference happens here at the two-parent crossover. So all the other steps are basically the same. We start the generation list, we generate an initial population, we split the chromosome to an X and a Y for the function. We have to do things like converting the binary string to decimal values, calculate fitness based on the function. We'll calculate a ratio. We'll compare the ratios. Are any of them negative? If they are, we're going to shift everything so that nothing is going to be negative and nothing is going to be 0. We're going to add that to a fitness list. Now that list is going to basically ask, is the entire population in the fitness list? If it's not, we're going to go around and come back, go through all the way until we have the whole thing. Then we will do a roulette wheel selection that is going to select the parents that have the highest fitness. And here's where the difference happens is two-parent crossover is going to select pairs and decide go through this whole process where they're going to get the pair, they're going to get the crossover probability. If there's a probability, then if it's supposed to happen by the probability, then you go to the swap. Basically select a random breakpoint, so you swap the chromosomes for the two pairs. If you calculate a mutation, if there is one, then you flip a gene randomly in that offspring, and then you add it to the list. Then if the crossover is not complete, you go back through and you get the next list. If the crossover does not happen, you simply copy the parents, and directly to the new population. You add it to the list, and once our crossover procedure is complete, once we've gone through all of the population, we'll return and we'll check if the runs are completed, and if not, we'll add this offspring to the generation list, and we will repeat the procedure with getting the next chromosome and repeating the whole thing again until we get to all the runs are completed, and we return Um, we return the values of what is the highest x, what is the fitness value that is the max, that, and what is the x and y for that highest fitness value. Now, the PWR algorithm is essentially the same. We're going to go through everything except in the very beginning we are going to generate these Pascal weights. So we'll get this Pascal triangle and the weights, and we'll use those to get everything else. And we'll use those in the PWR crossover. Everything else remains the same. We go through the whole procedure, we shift ratios, we don't want to have any negative values, and at the roulette selection wheel, we will select a value of some number of parents. By the paper's description, the best numbers, the most optimized, are between 3 to 7 parents. So we don't need to take the whole population, we just need to get 3 to 7 of them. Ideally 3 is better for speed, 7 gets you more exploration, anything more than that apparently is too conservative and doesn't really give you much better results for more time cost, for more overhead. So this is essentially what happens here. We are just doing exactly what we described. We're going to randomize the parents' positions. So if there was a list of 3, the 3 are going to be swapped to random order. We will get the first genes or alleles. We'll do this whole process of convert to binary, binary to probability. We'll convert from a probability to a logit, apply the weights, and get the sum. Convert that logit to a probability to a binary, add to the offspring gene, and then get the next gene, and keep repeating until we've accumulated all of them. At this point, now this repeats the rest of the genetic algorithm that I already showed with the 2 parent one. So calculate the mutation, get a mutation if there is one, flip a gene if not, just add it directly to the offspring list. If the crossover is not completed, then we can repeat this process. And one thing I did here was, instead of getting a new list of parents from the roulette wheel, I just chose to use the same parents but randomize the order. And so we'll repeat this until we have the full population. And once we have the full population, then we can return the offspring list and continue our process, where we can either we'll add it to the generation list and we'll get the next chromosome, repeat the whole cycle. Once we are done with all the runs and we have whatever number of runs we've decided, then we'll return the fitness value, the maximum fitness value, with the corresponding x and y. And so they are pretty similar. So I guess finally, this Pascal Weighted Recombination is a recent introduction. The paper was published July. Let's see. July 2025. So this was published this year. It provides a mathematical formulas to allow others to easily build this PWR operator, and I was able to build one of them. There are multiple families that do other things or that work in other spaces. It was easy enough to swap this operator for my own, and it worked just fine. The algorithm is based on Pascal binomial coefficients, and the whole purpose is to uniformly distribute around the center parents. Finally, the author was imploring that there should be more exploration in this area because there is a research gap with multi-parent recombination. So with that being said, I think I'm going to demonstrate my algorithm, and I'll just run the code. So what I've done here is, instead of just running the 200 times, what I've done is I've run the algorithm 200 times, then get the max value from that those parents, or from that generation list, and then I've put it into a max list where we're going to collect 200 more samples, and the maximum of the max list is going to be the value we use. So let's see, I'm going to run them all, and hopefully there's no problems. Hopefully everything goes well. Yeah, it's the ordering that is a problem here. Okay. Binary to decimal. Okay, that has gone, that has worked, that has worked. Probability. Okay. All right. So here we are. Unfortunately, it takes about 10 seconds or so, 11 seconds, 12 seconds to run through the 200 and 200. Oh, okay, it's a little bit longer, 16 seconds. And it comes pretty close. The first one is a two-parent recombination. The second is the PWR. And if I run it again, that's 16 seconds. So the values I'm getting consistently here are this for the two parents. The PWR recombination is giving me this different variables. So one thing I can do is adjust the number of parents. And so I've gone from 3, I will go to 4. I'll run that again. And let's see what difference we make from this. So our value comes a little closer, and if we do this again, but our time went up by 1 second. Oh, okay. So that's the algorithm. It is maybe because of my implementation that it's a little bit it's slower than the two-parent one, but the idea is the distribution should be more centralized, so that our weights through each generation is going to be somewhere in the middle of the parents. Thank you for your time. I will be uploading all these documents to the Canvas page.